Okay, I want you to picture something. A machine tucked away inside a refrigerator so cold it's literally colder than deep space, totally cut off from, well, everything. Inside is a quantum computer. But what if I told you this isn't about making a faster computer? Not really. This is something completely different.
Yeah, so right off the bat, we've got to get one thing straight. It's so easy to just think of these things as, the next generation of supercomputers, just faster. But that's not it at all. They don't even play by the same rules. It's a totally new way of thinking about information itself.
So that's the big question, right? If they're not just super fast calculators, then what are they? And to answer that, we actually have to go way back to the mind of this brilliant physicist who ran smack into an impossible problem.
All right, let's set the scene. It's the 1980s, and we're talking about one of the giants of 20th century physics, Richard Feynman. He had this amazing dream, but he was facing a massive roadblock. See, Feynman wanted a peek into the quantum universe. He couldn't just look at it, that would mess it up. So he figured, hey, I'll just simulate it on my computer. But he hit a snag, and fast. His classical computer just couldn't keep up. Every time he added just one more particle to his simulation, the amount of work his computer had to do didn't just go up a little, it exploded. It grew exponentially.
And this is where you really start to see the scale of the problem. Trying to simulate just a handful of quantum particles was a huge pain, but trying to model, say, a few dozen? Forget about it. It was literally impossible for a normal computer. The complexity was just mind-boggling. He realized that classical computers, the ones and zeros machines, were just the wrong tool for this job, period.
And then he has this incredible breakthrough, a totally revolutionary idea. He thought, instead of trying to force my classical machine to speak this weird quantum language, what if I built a machine that was already quantum? A computer that ran on the exact same laws of physics he was trying to simulate. And boom, right there in that moment, the idea of quantum computer was born.
So what does it even mean to be natively quantum? Well, it means you pretty much take the rulebook for normal computers and you just toss it out the window. You start playing a whole new game with a set of rules that are, well, they're a lot weirder. Okay, the absolute core of all of this, the heart of quantum mechanics and quantum computing, comes down to this one idea called amplitudes. Now, you can kind of think of them like probability, but there's a wild twist. Amplitudes aren't stuck between 0 and 1. They can be positive, or they can be negative. And that one little change, believe it or not, changes everything.
And here's why that matters so much. Think about it. With normal probability, things always add up, right? Your chances just get bigger. But with quantum amplitudes, a path with a positive amplitude can meet a path with a negative one, and they can completely cancel each other out. Poof, gone. This is called interference. And folks, this is the secret sauce. This is what makes it all work.
Okay, so we've got these weird new rules, but what are the actual building blocks? In a regular computer, we have bits. In a quantum computer, we have something way more interesting.
Everybody, meet the qubit. Now, like a classical bit, it can be a 0 or a 1. Simple enough. But, and this is a huge but, because it's playing by those quantum rules, it can also be in a state called superposition. What's that? It's basically being a mix of both 0 and 1 at the exact same time. It's not one or the other until the very last second when you actually measure it. And that lets it hold so much more information.
And just when you think it can't get any weirder, it does. When you bring qubits together, they can become entangled. This is this deep, almost spooky connection between them. The source material had this great way of putting it. Imagine a book where every single page is just random nonsense. The information isn't on any one page, it's hidden in the patterns and connections between all the pages. That's what entanglement is like. The real power isn't in the individual qubits, it's in their relationships.
So let's talk about what this really means for scale. I'm just going to give you a number, 500.
Just hold that number in your head. Now imagine you have a system of 500 entangled qubits, all of them connected, all of them sharing information in those complex correlations. If you wanted to write down the complete description of that system using a classical computer, well, you would need a truly ridiculous number of bits.
You would need more bits than there are atoms in the entire known universe. No, I'm not kidding. More bits than atoms. This is exactly what Feynman was talking about when he said classical computers just can't scale for this stuff. We're not even in the same ballpark anymore. It's a completely different kind of information space.
Okay, so this is the crucial part. We've got this gigantic computational space thanks to superposition and entanglement. Amazing, right? But
There's a catch, a big one. The second you actually look at a qubit to see what it's doing, its superposition just collapses. It snaps into a plain old 0 or 1. So how on earth do you get a single useful answer out of all that?
Yeah, that's the central puzzle, isn't it? The system is holding all the possible answers at once in this beautiful, complex quantum state. But if you measure it and just get a random result, what's the point? You need a way to guide it to the right answer.
And the solution, so elegantly, comes from that same bizarre quantum rule we talked about just a minute ago, interference. The fact that positive and negative amplitudes can just cancel out.
You can think of a quantum algorithm as this carefully choreographed dance. So, step 1, you start with all your qubits in superposition, basically representing every possible answer at once. Step 2, you use what are called quantum gates to tweak and shift their amplitudes. And here's the goal. You choreograph it so that the paths leading to all the wrong answers have amplitudes that cancel each other out, while the paths leading to the right answer, they reinforce each other. They get stronger. So at the very end, when you finally measure the system, the chance of it collapsing into the one correct answer is super, super high. That's your winner.
Now, designing these algorithms is incredibly hard. We've really only figured out a few big ones so far. And that brings us to the final question. What is all this incredible power actually for?
Well, right now, today, their most solid use is exactly what Feynman first imagined, simulating quantum physics. Just helping us get a better handle on the fundamental rules of our universe. Now, you hear people talk a lot about cybersecurity or finding the best solution to complex problems, and that's all really exciting stuff, but whether any of that is practical anytime soon, that's still a huge open question. For physicists, though, it's game on.
And that really leads to this one powerful idea. The honest truth is we are at the absolute beginning of this technology. It's like we're in the 1940s with the first classical computers. We can't possibly imagine all the ways they might change things. The most important use for quantum computers is almost certainly something that no one has even thought of yet. Think about it. For centuries, we've been trying to understand the universe using tools that don't really speak its native language. And now, for the very first time, we're building a tool that does. So the real question isn't just about how do we make faster calculations. The real question is, what are we going to discover? What mysteries of the universe will we finally be able to unlock now that we can finally ask nature the right questions in its own language?